In the last video, we learned the definition that A and B are congruent mod n if n divides A minus B. So let's do a proof using this definition. Suppose that k, a, and b are integers and that n is a natural number. If ka and kb are not congruent mod n, then n does not divide k. Okay, so let's think about this for a moment. What we are trying to show is that if ka is not congruent to kb mod n, then that implies that n does not divide k. So we see this might be a good opportunity for a contrapositive proof because, again, we're starting with something where assuming the hypothesis doesn't tell us a lot. So ka not congruent to kb mod n. What does that tell us? That tells us that it is not true that n divides ka minus kb. So it tells us that n does not divide ka minus kb. So ka minus kb is not equal to nc for any integer c. Where to go from there? That's not a very helpful statement, and therefore it would be worthwhile to try a proof by contrapositive. So why don't you try that out? Pause the video and try to do a proof by contrapositive of this statement, and we'll talk about it in just a moment. Okay, so we want to prove this by contrapositive, and let's just keep a little piece of scratch paper on the side in case we need it. So proof by contrapositive. All right, so when we're doing the contrapositive, we're going to always assume not Q. So we're doing not Q implies not P. That is what we are showing. And in this case, not Q is, it is not the case that n does not divide k. So in other words, n does divide k is not Q. So suppose that n does divide k, then that means that k is equal to n times t for some integer t. That's the definition of n dividing k. Now let's see, what are we trying to show? We are trying to show that this implies not p. We're trying to show the negation of ka is not congruent to kb mod n. So we were trying to show the negation of that. In other words, we're trying to show that ka is congruent to kb mod n. So that is what we were trying to show. It's not immediately clear how to do that from what we have so far, so let's just keep thinking about what this actually means. So what's the definition of ka being congruent to kb mod n? That's true if and only if by definition n divides ka minus kb. And when would that be true? That would be true if ka minus kb is equal to n times s for some integer s. So that is what we are trying to show. So this is what we want to show at this point, whereas what we know at this point is that k is equal to n times t, where t is an integer. So could we somehow use what we know already to get to this statement? So I need ka minus kb. Over here, all I've got is a k. What could I do maybe to turn this equation into what I see above? I could multiply both sides of that equation by a minus b. K times a minus b is equal to nt times a minus b. That's a valid thing to do. And then I have ka minus kb is equal to n times ta minus tb, where ta minus tb is an integer. Okay, so that is my path forward here. So now that I've done that on the scratch paper, let's do it in the actual body of the proof. So let's consider k equals nt and multiply both sides of the equation by a minus b. So doing that gives us k times a minus b is equal to nt times a minus b, and this implies that ka minus kb is equal to n times ta minus tb, where ta minus tb is an integer, and therefore, by definition, it is the case that Ka is congruent mod n to Kb. And at this point, we could make a statement about how that is the contrapositive of what we originally wanted to show, or we could just end our proof there with the assumption that our reader understands the contrapositive proof technique. Okay, let's do another proof using this definition. So let's prove the following. If a minus c is not congruent to b minus d mod n, then a is not congruent to b mod n, or c is not congruent to d mod n. So give that a shot and we'll talk about it in a moment. Okay, so let's try approaching this proof using the contrapositive proof technique. So we are going to show that not Q implies not P. Let's just think about what is not Q in this case. Not Q is, it is not the case that A is not congruent to B mod n or C is not congruent to D mod n. So it is not the case that A is not congruent to B or C is not congruent to D. So remember that when we negate an or statement, we get an and statement. So we negate each of the statements. A is not congruent to B, and it is not the case that C is not congruent to D. So in other words, this is equivalent to A is congruent to B, and C is congruent to D, and these were both mod n. So again, this is using De Morgan's law, and so that is our negation of Q. So proof by contrapositive. Suppose that A is congruent to B mod n and C is congruent to D mod n. So that is our assumption. Then, by definition, it is true that A minus B is divisible by D, or in other words, n divides A minus B, and n divides C minus D. So let's further unravel that. That means that, therefore, again breaking apart a definition, n divides A minus B means that A minus B is equal to nt for some integer t, and C minus D is also equal to n times some other integer s for some integer s. Okay, so now we've broken apart the hypothesis. We've broken apart not Q. And let's try to think about what we want to show. So WTS, want to show not P. In other words, we want to show the negation of A minus C is not congruent to B minus D, which is A minus C is congruent to B minus D mod n. So what is the definition of that? That would be true if n divides a minus c minus b minus d. In other words, that's true if and only if a minus c minus b minus d is equal to nk for some integer k. So that is what we are trying to show. So back in the actual proof, let's consider a minus b minus c minus d. So let's consider that quantity. And we see that above, by substitution, that's equal to nt plus ns. And that is equal to n times t plus s, where t plus s is in the integers. And so what have we shown? We have shown exactly what we wanted to over here. So therefore, it is the case that n does divide a minus b minus c minus d, all in parentheses, and is dividing that entire expression. And so it is the case that a minus b is congruent to c minus d mod n. And we have shown what we wanted to by the contrapositive. We have shown not p. And so we are done. So far we have proven statements of the form, if p is true, then q must be true. And we've seen two different methods for doing this. The first was the direct method of proof, in which we assume p is true, and we use whatever definitions, theorems, algebra, logic we can to conclude that q must be true. The next technique that we have been working with is the contrapositive proof technique. And it works because not q implies not p is logically equivalent to p implies q. And when we use that technique, we assume not q is true, and we do whatever definitions, logic, algebra, etc. We need to eventually conclude that not p is true. So one question you might have is when to use each of these different techniques. And you might have noticed that in general, when we use the contrapositive proof technique, that tended to be in situations when p does not tell us much. So when p doesn't tell us much, that's immediately useful. So for example, if we have a statement p like n does not divide k, all right, so k is not equal to n times c for any integer c. Well, there isn't a whole lot to do, just knowing that something is not true, knowing that nc is not equal to k for any integer c. There's not necessarily an obvious follow-up to that. So most of our proofs so far, the second line has been to expand whatever definition comes from either p or not q. So in both cases, we are expanding whatever definitions we have, and then from there, thinking about what we are trying to prove and how that might relate to our expanded definition. It doesn't mean that every proof will always go that way, but many proofs do. So when you're thinking about direct versus contrapositive, what you can always do is think about what it means for p to be true, what that definition means, and how might that definition relate to your desired conclusion. And if you're stuck, then something to try is the contrapositive proof technique. Think about what not q means, expand that definition. Think about how you might find not p. You might also want to expand this definition and think like in a larger way about what this means and what kind of relationship there is between not q's definition and not p's definition. So those are two proof techniques. The next chapter we'll be talking about the method of contradiction. So we'll be able to prove statements of the form if p then q, as well as other statements that do not have that form.